Welcome to ePadasala lecture series in computer science. Today we are going to discuss about approximation algorithms. Probably last module you can recollect we introduced the concepts of approximation algorithms where we designed algorithms for NP complete problems. We said most of the real world problems are NP complete in nature. Therefore, it is very difficult to design algorithm for that, and for those sort of problems we can go for approximation algorithms. In this module we are going to discuss more about approximation algorithms. The learning objectives of these particular modules are as follows. We will understand what the approximation algorithms are. We will try to set a context for the approximation algorithms. Then we will try to understand some basic approximation algorithms. Last module we were talking about some problems like traveling salesman problem. We were talking about problems like set cover, vertex cover, etc. Today also we will discuss some of the basic approximation algorithms, and most importantly we will also talk about various design principles such as the heuristics, greedy approach and dynamic programming for designing approximation algorithms. What is an approximation algorithm? Probably you can recollect last module we introduced these principles. For NP complete problems there is possibly no polynomial algorithm to find optimal solution. We discussed lots of problems like traveling salesman, Hamiltonian problem, knapsack problem. We discussed about sum of subset problem in earlier modules. These problems are NP complete in nature. That means these algorithms do not have any algorithm that is polynomially that can be run in polynomial time. In other words, the algorithms are exponential in nature, and if instances becomes more and more, the algorithm complexity becomes more, and it is very difficult to solve this problem within the available computer resources. For these sort of problems only we are going for approximation algorithms. The idea of approximation algorithm is to develop polynomial algorithms to get near optimal solutions. Probably you can recollect in the last module I said there are many problems for which exact solutions are possible. Most of the algorithm we discussed as part of this course do have some exact algorithms, but there are also some of the problem for which the exact solutions are not possible. These problems can be solved to get the approximate or near optimal solutions. Near optimal solution is more than sufficient for most of the problems because it is almost as closer to the original solutions. So, these sort of problems where finding the solution is very difficult can be solved using approximation algorithm to get the near optimal solution, which is more than sufficient for most of the circumstances. That is the reason why approximation algorithms are becoming very popular. What is the criteria of approximation algorithms? Approximation algorithm should run in polynomial time. That is the most important issue. Second thing is these algorithm is supposed to give solutions which are more closer to the original solutions. So, in that case we have to define a parameter called approximation ratio. The best parameter of approximation ratio is to find the difference between the original and approximate solution. If that is a constant one, then we can say that approximation algorithm is the best. But most of the time finding the difference is very difficult. So, in other words, writing an approximation algorithm to get the constant difference is very difficult. In other words, on the contrary, it can be uh, easier to write those algorithms with the approximate ratio in multiplicative terms. In other words, if the cost of the optimal solution is C star, and if the cost of the uh, solution that is produced by the approximation algorithm is C, then we can take the ratio of C to C star and C star to C, we can find the maximum, and that is called the approximation ratio or rho of n. So, the algorithms which are said to have the approximation ratio of rho of n is often called as rho of n approximation algorithms. So, we will discuss now about designing approximation algorithm for various problems using various principles. The first principle we will talk about is called the heuristics. What is the heuristics? Heuristics are nothing but the common sense based rules. So, based on our experience and intuitions, we can design various thumb rule, and using these thumb rule we can formulate the solution for the given algorithm. So, the algorithm that are based on heuristics do not guarantee a feasible solution. In other words, these algorithms normally work, but sometimes these algorithms may fail also. These algorithms may possibly take the exponential time. So, in that case we have to experiment these algorithms to try out whether the approximation solution is possible or not. We will discuss some of the heuristic based algorithms. So, last module we introduced the problem of traveling salesman. So, you can recollect the problem. We have a undirected graph. So, the graph is having a set of vertices V, and we have a list of edges E. So, the question is we have to find the shortest path, that is the least cost tour, where we have to start from a city, then we have to visit all other cities exactly once, and then we have to come back to the original city where we have started. This is called a tour, and our main objective is to find the least cost tour. So, probably you can say that these problems can be solved in greedy approach, dynamic programming, or backtracking. We have seen all those solutions in the previous module. But what needs to be noted is that this problem is NP complete. What does it mean? It means that if the number of cities becomes more and more, then the complexity of the algorithm becomes more, and it is very difficult to solve these sort of problems. In other words, these problems are called the NP complete problems. We can approach these problems with approximate solutions, where we can use some sort of an heuristic. We will use a heuristic called the nearest neighbor heuristic. What does it mean? It means that you are in a city and then you are trying to find the nearest neighbor, and then you try to go to that particular nearest city. So, based on this intuition or experience, you can design a algorithm which can be called as the nearest neighbor heuristics. So, you can see exactly how this algorithm works. So, you are starting with an arbitrary node as the starting vertex, then you try to find the nearest city and try to visit it. In other words, visit all the nodes using the nearest neighbor rule, and then you try to return to the original vertex from where you started, and finally you return the tour and exit. This kind of algorithm is called the nearest neighbor heuristics. Maybe you can change this criteria and you can design lots of other algorithms similar to this. Maybe what I can do is, instead of visiting the nearest city, maybe I can automate that by arranging the edges. So, in multi-fragment heuristic method, what I am trying to do is that I am trying to sort all the edges in ascending order based on the weights of the edge. I start from a city, then I choose the next edge from the sorted edge, and I am trying to add that if that edge is possible. So, I repeat the steps 1 and 2 till a tour of given list of V vertices are obtained. Third algorithm is called the Christofides algorithm, which is similar to the algorithm which we discussed in the last module. This is also based on the concept of what you say minimum spanning tree. So, you are given a graph, so you try to construct a minimum spanning tree. This can be done using either Prime's algorithm or Kruskal algorithm. Let us use the Prime algorithm to construct the minimum spanning tree. Then add edges of minimum matching to all odd degree vertices of minimum spanning tree. So, try to add edges of minimum matching to all odd degree vertices of the minimum spanning tree. So, you form multi-graph by adding the extra edges and find Eulerian circuit. Eulerian circuit is you start from a city, you visit all the edges exactly once, and then you come back to your original city. Then from this you try to construct the Hamiltonian circuit and output that as a traveling salesman tour. Heuristics are nice way to design approximation algorithm, but as I said earlier, heuristics normally work, but occasionally it may fail also. So, we have to take care of this particular point. In other words, no heuristic based algorithm can guarantee the solution. Therefore, we have to look for the other approaches for designing approximation algorithms. One possible approach is called the greedy algorithm. Probably you can recollect in earlier modules we were talking about the greedy approach, where we are trying to find the optimal solution of the given problem. You can see the procedure: find a set which is cost effective. So, add S to the solution set if feasible, then you try to repeat till all the elements are considered. So, you can see the steps are you have selection procedure, then you have feasibility check, then if the solutions are feasible, then you try to add that into the solution set, and finally you have the solution check whether all the elements are considered or not. If so, you try to exit. We will take one simple example of knapsack problem, and then we will try to design a approximation algorithm. Let us assume that we have n objects. We have n objects each of weight Wi. Each item has got a profit P of I. So, that means if items are A1, A2, A3 etc., then weight is size of AI and profit is what you say profit of AI, and you have one knapsack whose capacity is capital B. You can say that greedy knapsack problem is a problem where we have to load the knapsack with all the items so that we can maximize the profit. So, the mathematical formulation of the problem can be given something like maximize we have P of I and X of I, where X of I is the given item list, something like A1, A2, we have X1, X2 up to X of n. So, we have to maximize the profit subject to the constraint that the maximum capacity should not go beyond capital B. This is the mathematical formulation. Fine, how to design a greedy algorithm for this? This we discussed earlier also. You can load the knapsack with various items based on many criteria. So, based on the weight I can load, based on the profit I can load, and we had seen that the best way to load the knapsack is based on the criteria of Pi to Wi. So, you take the ratio of Pi to Wi and sort it in the non increasing order. So, put that into the knapsack according to the sorted sequence as possible as we can. So, this has to be repeated till the constraints are fully satisfied. You can take a numerical example. Let us assume that we have 3 objects. The capacity of B is 20. For 3 items, the profit is 25, 24, 15, and the weights are given as 18, 15 and 10. So, you can see the ratio of Pi to Wi gives 1.32, 1.6 and 1.5. So, now you can see based on this sorted sequence. So, I am trying to load the knapsack. So, that means you can see very well P2 to W2 is maximum 1.6, therefore, I load the knapsack with item 2, and the remaining thing is loaded with the item 3 because the ratio of P3 to W3 is maximum. This is what the greedy algorithm is all about for the fractional knapsack problem. You can design this sort of algorithm for many problems, problems like bin packing. Bin packing is similar to the knapsack problem where you have items x1, x2 up to x of n, each is having some weight Wi. So, the problem is you have to pack the maximum number of items into the finite number of bins, each with some capacity Bi using the minimum number of bins. So, sometimes the bin can be a single bin also. Another problem you can design is sum of subsets where you have a finite set x1, x2 up to xn. So, this is for n numbers. You have to find subset S prime that maximizes the sum with the constraint that sum is less than or equal to k. In other words, if I am having a set something like 5, 10, 15, 20, 40, etc., if I am saying that integer is 25, then I have to find all the sets that satisfy these constraints. So, that means I can take a set of 10 and 15 as a feasible set, because 10 plus 15 is going to be 25. So, that is what given k. So, sum of subsets is another problem where you can design these sort of greedy algorithms. Another way to design approximation algorithms is by using the linear programming method. So, linear programming is a established study called operation research in mathematics, where we try to solve problems of resource allocation. You have lots of requests, you have what you say very meager resources. So, you have to maximize the allocation such that all the requests will be fulfilled. So, linear programming is a problem of optimizing a linear function something like z. So, this can be a maximization of z or minimization of z subjected to a set of constraints that can be modeled as the linear inequality constraints. So, that means all these constraints will have the lesser than or equal or greater than or equal to sign. So, the function is being maximized or minimized, in other words, in short, optimized, is called the objective function. All the constraints are stated as a linear formula. So, that means the function with the constraints in linear form is called the linear programming. Any assignment of the variables that satisfy the constraint is called what you say the feasible solutions. The linear programming guarantees the optimal solution of the given problem most of the times. This is a template of a linear programming, where you can see you have an objective function 7x1 plus x2 plus 5x3. You have to minimize this subjected to the constraints. You can see that all these constraints are given in the form of an inequality, like greater than or equal to or less than or equal to. You can see in this problem all are given as greater than or equal to some numbers. So, all the constraints are of the type greater or equal in minimization problem, and if it is a maximization problem where you have everything in less than or equal to. One of the important point to note down is all these variables are constrained to be non-negative. So, that means you can use some simpler transformations, and you can easily convert the word problems into the standard format of maximization or minimization subjected to all these constraints. Integer programming is similar to linear programming, except that all these variables must be integers. These problems are called as integer programs. Only difference is in linear programming fractions are allowed, but whereas in integer programming fractions are not allowed, it has to be integers. The problem that we discussed in the last module, like set cover problem, vertex cover problem, can be easily modeled as what you say a linear programming. So, probably you can recollect in the last module we discussed that in vertex cover the aim is to choose the minimum number of vertices to cover all the edges, and we can easily model that in the form of an integer, and we can solve these using some of the conventional techniques like the simplex method, etc., etc. Similarly, the set cover can be modeled as a linear programming. So, in other words, all the problems can be easily converted to the linear programming format. So, the procedure is very simple. If a problem is given, fine, we can solve that problem if it is an optimization problem using integer programming. So, your integer programming are very difficult to solve, therefore, you relax integer programming to linear programming. Then you try to find the optimal solutions using linear programming. So, you will get a lot of fractions, then you try to round off fractional solutions deterministically or approximately, what you say, to get the approximate solution for the given problem. So, this is the kind of approach we will be using for designing approximation algorithms. The last approach for designing approximation algorithm is called dynamic programming. Probably you can recollect in earlier modules we were talking about exclusively about dynamic programming. So, in this approach what we will do is we will try to find the pseudo polynomial algorithm for solving a given problem. So, in other words, if the instances are smaller, then the problem can be solved. For example, TSP problem can be solved if the number of cities is very less, something like 10 or 12. So, the algorithm that is used to solve these problems are called the pseudo polynomial algorithm. Then you try to trim or scale down the input by rounding it off. So, that means in a main problem you try to scale the input, then you try to solve that problem using dynamic programming to find approximation solution for the modified instances. The kind of algorithm that uses the dynamic programming approach to solve these set of problems are called PITAs, that is polynomial approximation scheme algorithms, where you can have lots of algorithms, not a single one, but many algorithms, and these algorithms are 1 plus epsilon approximation algorithms, where its running time is bounded by a polynomial in the size of the instance. So, these kind of algorithms are called PITAs, and you have fully PITAs. So, the same as above, plus time is bounded by a polynomial in both the size of the instance 1 and what you say 1 by epsilon. In other words, in short, lots of algorithms are possible with different values of epsilon. So, we will take the knapsack problem and then we will try to see how this is approached in what you say dynamic programming. So, we are given a set of items A1, A2 up to An, and as we have said earlier, the objects have got weight, that is size of Ai, and profit of Ai. So, the maximum capacity is capital B. So, the problem is to find the subset of objects whose total size is bounded by B. In other words, the aim is to maximize the profit. Remember, in earlier version we tried to solve this problem by designing various recursive equations. So, A of I comma P is to denote the minimum size to achieve profit using the objects from 1 to I. So, if we do not choose the object I plus 1, then this is what the condition, and if we choose this, then this is the constraint. So, we have to choose the minimum of this. So, probably you can recollect in dynamic programming what we were doing is we formed a table and we started recursively filling this table, and the objective of using this table is to reuse these values so that the values of the next row or column can be computed. The objective is to use reuse rather than recomputing. So, in approximation algorithm, what we will try to do is we will try to scale down the numbers and we try to compute the optimal solution for this modified instance. In other words, if you have 100 and if you want to trim that 10 by 10 times, then you try to divide that 10 to get 10, and you for this minimum numbers you can find a pseudo polynomial algorithm. That is the key. In other words, the worst case the algorithm complexity will not change by the factor with which you are trying to divide the original number. So, the logic is very simple. You try to scale down so that you have n columns and at most np columns. So, your total complexity is what you say order of np. So, that means you have a pseudo polynomial algorithms. So, you can see the algorithm. So, given epsilon, what we are trying to do is you try to scale the profit, where p is going to be the largest profit of the object. So, for each object you can see that the profit is also getting trimmed, and using these trimmed values we are trying to find the conventional dynamic programming algorithm to find the most profitable set S prime, and finally we are returning S prime as the approximate solution. So, this is PITAS. So, that means you can say the goal is to find a solution which is at least 1 minus epsilon opt for any value of epsilon greater than 0. So, this is what the final algorithm will look like. So, we try to modify, then we try to apply the dynamic programming to compute the optimal solution, and then we try to output what you say S as the approximate solution. What is the complexity analysis? So, we are trying to trim it. So, that means you can see the complexity time is order of n square, floor of p divided by k. So, that means it is going to be order of n cube by epsilon. So, this is what your what you say algorithm analysis is going to be. In short, in summary, we can say that the heuristics can be used to design an approximation algorithm. Greedy approach can be effective for designing approximation algorithms. Dynamic programming approach can be used to design approximation algorithms, and for some problems linear bar integer programming can come very handy for designing approximation algorithms. These are the references. Thank you very much. Thank you for being with me for this time.